Chernobyl was supposed to be a quiet Soviet nuclear power plant, supplying electricity like any other. Instead, one late-night test in April 1986 blew open a reactor, sent a radioactive cloud across Europe and created the most infamous nuclear disaster in history. On paper, it was just a safety experiment. In reality, it was a perfect storm of bad reactor design, ignored rules, and one button that made everything worse instead of safer. In this video, let's break down in simple engineering terms what Chernobyl's reactor was, what the operators did that night, and how one test turned into an explosion. Chernobyl Unit 4 was an RBMK nuclear reactor, a Soviet design that used uranium fuel, water as coolant, and graphite blocks to slow down neutrons. Most Western reactors use water to both cool and help control the reaction, but the RBMK used graphite as the main moderator, which made its behavior very different. Here is the simple version. Inside the core, uranium atoms split, releasing heat and neutrons. Graphite slows those neutrons so they can hit more uranium atoms and keep the chain reaction going, while water flows through channels to carry away heat and turn into steam for the turbines. This design had two hidden problems. At certain conditions, when water turned into steam, the reactor power increased instead of decreasing. Engineers call this a positive void coefficient. The control rods, which were supposed to quickly shut the reactor down, had graphite tips that caused a brief spike in power when they were inserted from the top. On a normal day, automatic systems and procedures kept these risks under control. On the night of the test, almost every protection was turned off or ignored. The plan for the night of April 26, 1986 was to run a safety test. Engineers wanted to know if, after a power cut, the spinning momentum of the turbines could keep pumps running for a short time until diesel generators started. To do this, they needed the reactor at a lower power level. But due to delays and operator actions, the power dropped much lower than planned, to a very unstable region, only a small fraction of full power. At low power, the RBMK had another problem, a buildup of xenon-135, a poison that absorbs neutrons and kills the reaction. To fight this, operators pulled out many control rods to force the power back up, violating safety rules that required a minimum number of rods inside the core. At this point, the reactor was at low, unstable power, with too many rods removed, with several automatic safety systems disabled, and water flow conditions that made it sensitive to any change. In other words, the reactor was primed like a loaded spring. Around 1:23 a.m., the operators started the actual test. They closed steam valves to the turbines. As the turbines coasted down, pump power fell, water flow through the core decreased, and more water turned into steam bubbles, voids, inside the fuel channels. In an RBMK, those steam voids increase reactivity. Less liquid water means fewer neutrons get absorbed, so more neutrons keep the chain reaction going, and power starts rising. The reactor began to run away. The automatic systems that should have stopped this were disabled or limited, and the core conditions were already outside the safe envelope. At 1 hour 23 minutes and 40 seconds, someone pressed the AZ5 button, the emergency scram that should instantly shut the reactor down. All control rods started moving in from the top, but because of their graphite tips, the first part of the movement actually pushed water out and replaced it with graphite, briefly boosting reactivity in the lower part of the core. In that unstable state, this was fatal. Power spiked to many times the rated level in less than a second, fuel channels ruptured, superheated water flashed into steam, and a series of explosions blew apart the core and the 1,000-ton reactor lid, exposing burning graphite and fuel to the open air. There was no containment building like in many Western reactors, so radioactive material shot straight into the atmosphere. Inside the plant, workers and firefighters saw pieces of glowing graphite on the ground and a blue glow from the destroyed reactor, not realizing how dangerous the radiation was. 2 workers died that night from injuries, and dozens of firefighters and staff received massive doses of radiation in the next hours, many of whom later died from acute radiation sickness. The nearby city of Pripyat, built for plant workers, was not evacuated immediately. People woke up to strange dust and helicopters overhead, and only about 36 hours later were buses brought in to evacuate the entire city, which has remained an abandoned, ghost city ever since. Over the following days and weeks, radioactive clouds spread over parts of the Soviet Union and Europe, triggering alarms in other countries and forcing authorities to admit something had gone terribly wrong. After investigations, experts concluded that Chernobyl was not just operator error or just bad design. It was a combination of flawed reactor physics, poor safety culture, and a system where rules could be bent without anyone saying no. Key engineering lessons were: never allow a power plant to operate in unstable regimes just to complete a test or meet a schedule. Reactor designs must fail safe. Emergency systems and control rods should never be able to make things worse. Safety culture is not only about equipment, it is about training, open reporting, and the authority to stop experiments when conditions are risky. After Chernobyl, RBMK reactors were modified, international nuclear rules were tightened, and safety culture became a central concept in nuclear engineering worldwide. Chernobyl is often used as a symbol that nuclear is dangerous. But for engineers, it is also a case study in how small design decisions and ignored procedures can line up into a disaster that affects millions. If you want more videos where complex failures are broken down in simple engineering language, tell in the comments which project should be next: another nuclear plant, a dam, a bridge, or a megaproject closer to home.